if you have any problems hearing me or seeing anything, let me know as always. All right. So like I said last week, the plan for today is to wrap up the rest of the air engine project. So we'll try to do that. And at the beginning, I'll talk to you a little bit about some applications of what we're doing here.
I forgot to do the homework because yeah.
Yeah, all right. I'll take a moment for questions about the homework and things like that. Or I can go through things that you had trouble with or show things that you want to see after this brief introductory part. So yeah, hold on to your questions. All right, so what we've learned in this class so far is using Onshape, right? The stuff you have here. We've learned how to basically make a 3D model, either from something that you're matching in your own mind or from using a drawing. And we've hopefully had a lot of practice using these different drawings to make parts and assemblies. So in the last 2 weeks of class, and I guess kind of including this one, we're going to talk a bit about manufacturing, which is kind of the next step that you would go in most cases when you're trying to create something, right? So you start out by making a model, a design on your computer most of the time, and then you'll actually create the thing that you designed by some way, right? And how do you do that? If you have some experience in like a machine shop, a wood shop, if you use, maybe at your school, they offer a class or a workspace where you can use tools. You may have had some experience making things before, right? So if you're really lucky, maybe your school has a 3D printer. Other common things, a lot of older tools especially, are things that would fall under what we call conventional manufacturing. So if you have a wood shop, the standard tools there, you probably have a bandsaw and a drill press at least. So often when you go, like as you get a bit older and you continue to work in some kind of engineering discipline, you'll start to get introduced to a few more different tools, which are very standard, especially in terms of like education as a mechanical engineer, for example. You're probably going to learn to use two machines that I'm going to talk a little bit about, which are the milling machine and the lathe. Other processes that you might use include laser cutting and the water jet. And as you start to expand the number of tools you have access to, more and more you'll be able to create things like this air engine in real life using like materials, using things like plastic or wood or metal. So why did I call these things conventional manufacturing? In this class, and a lot of the time when you're working with CAD, what follows is usually 3D printing, and it makes a lot of sense because 3D printing is really powerful and at this point a really simple way to create in real life these objects that you design on your computer. You might have heard of rapid prototyping, which is the ability that these techniques like 3D printing give you to basically almost instantly create the thing that you design, see if there are any problems, hold it in your hand, see it in action, and based on that to iterate and continue to design things. So this additive manufacturing, this is not what we usually call conventional manufacturing. It's like a, if you've ever seen a 3D printer, the way they work is that they will build the object up by adding material a little bit at a time. So there's a lot of different ways well, a lot of different devices, techniques that fall under the umbrella of additive manufacturing. Some of them look completely unlike what you imagine when you see a 3D printer. But the principle is the same, where you build the whole object a little bit at a time, kind of by slicing it up and just adding on a layer of material at a time. And the stock for the material, it can come in different forms. For most like plastic desktop hobby 3D printers, you might have a process like fused deposition modeling, where you have like a spool of plastic that gets fed into a heated nozzle, and you just get like a steady stream of this plastic that just flows out of the nozzle as the head is moving around in 3D space. Some more exotic or high-tech methods of 3D printing that are still called 3D printing might have something like powder bed fusion. So it's the same idea. You're still adding on material one layer at a time, but instead of squeezing out plastic out of a tube like toothpaste, what you're doing is you have like a bed of powder, and at every layer you just like draw the next layer on. It's metal powder, and then you draw on the next layer with a laser, and the laser melts the metal powder onto your build plate and eventually onto the part that you have. And every time you just lower the bed and you add more powder. So pretty interesting. This is a technique that they use for like industrial parts made out of metal. This is sort of like 3D printing. But the idea is you can, I'm not sure what the printing version is called, but there's a technique where you can have like a liquid of some kind of plastic, and by exposing that plastic to enough intensity of light, you can make it harden. And so that's another kind of additive technique where we have these kind of novel methods where we're building the material by adding this material. And that's in contrast to subtractive manufacturing. So when we talk about conventional manufacturing, we're usually referring to these subtractive manufacturing techniques. So machining, that's the classic example. You're starting with some like stock material, like you might refer to as billet. You just have these like big blocks of material, right? And you start with that, and then the final part, it's like creating a sculpture. You're just chipping away, you're just carving away, cutting away material from these big blocks until you have what you want left. And it's a very common way, even in prototyping. You would make a lot of things like this. There's also a lot of, like at scale, you don't machine a lot of things, but you might use methods like casting. But that's kind of what we're trying to distinguish here. So subtractive manufacturing, if you have like a wood shop class at your school, that's kind of what you're learning there. I'd highly recommend taking that type of class because it's really fun just to make some things with your hands. As you continue to take that kind of class, or you study maybe mechanical engineering, you'll start to learn about two types of machines. First being the milling machine, and the second being the lathe. So I have some pictures here that kind of show what's going on here. For a milling machine, you have this block of metal. Like I said, you start with some billet, and you're cutting away material from that billet to get what you want. So you have a cutting tool here. This spiral shaped thing, it's called an end mill. That's your cutting tool. So this spins really, really fast. And whenever it touches your piece of billet, it just cuts away the metal that's there. This is another picture of a machine like that. You can see that the tool is animated, it's spinning. And whenever it touches the metal, that's when it's going to remove that material. So that's how you make a part. We also have something called a lathe. So this is kind of like the opposite mentality. It's the complement, right? Instead of spinning your cutting tool, you actually spin your work. So you start out with a big rod of your material. This is the thing you're trying to make. And then you just hold up your tool against that spinning material, and that'll just carve away material because it's spinning against your tool. So you use this to make rotationally symmetric parts. For example, in a car, like a lot of your rotating components are going to be circular. So you'd start out by turning something on the lathe. And these materials, like they can be metal, they can be wood, foam, a lot of different types of mills and lathes. For example, if you are very interested in like watching people make stuff, you can find a lot of videos of people turning something on a wood lathe. So I'll leave it as an exercise to you to maybe look into it a bit more, but it's, you can find people making things out of wood just by putting it on their lathe, on their chuck. They spin it up really fast. So you just have this huge spinning block of wood, and then they use their hands. They hold like tools, like chisels or various sharp implements up to the wood to make these nice patterns. So furniture making, I think chess pieces are pretty cool. But there's a lot of really great machining content out on the internet, on YouTube and such, and it can be pretty fun to watch. So I'd recommend giving it a shot. Other things, these machines can be manually operated. So they have dials that you have to spin with your hands, and you kind of have to measure how much you're turning using the dials. But these days we also have what's called CNC, so computer numeric control. And this is kind of a general term. Your 3D printers are also like CNC. The computer is telling the stepper motors inside your 3D printer, for example, exactly how much to turn to move around in space. And so that it always knows exactly where in space it is. And so at the low level, what the machine is getting whenever you upload like a STL file of your 3D model to the printer, at some point you're going to have to convert that 3D model into a set of instructions for the computer to read, because at the end it's a computer that's doing the work of telling the machine how to move. So it'll eventually be converted into something called G code. If you're curious, you can look into that. You can read about that. It's pretty abstruse, perhaps, but it's also like human readable. Like if you study it enough, you can actually understand what G code means. But it's just a bunch of different instructions that are standardized. So any machine standardized enough, like each machine will have a slightly different flavor, but there are programs out there that help you convert your 3D model into a set of G code instructions. And then you just upload that onto the computer knows what to do, and it just starts moving the machine around to do what you asked it to do. Yeah. So another thing that you might want to eventually start learning, what we're doing is computer-aided design. So we're making these 3D models on our computers. Another kind of field of things you can learn is computer-aided manufacturing. So that's what I was talking about when you're trying to create these instructions for the computer to read. Your starting point there is going to be a 3D model, and then you're going to use the computer software to kind of generate these different tool paths. Maybe you're kind of trying to make it as efficient as possible, but you're basically programming the machine, telling it what to do, and that would fall under computer manufacturing. And as the last thing, we started out here, this is like a discussion about applications of CAD. So if you're really into the engineering side of things, another place where you really need to have these 3D models that you make in CAD is in analysis, right? So in SolidWorks, or sorry, in Onshape, there's nothing stopping you from designing whatever you want, even if that's not physically possible, right? Like last week, we talked about the interference detection tool. There's nothing stopping you from making something not physical. We have like two objects that are like bumping into each other, crashing through each other. So taking that one step further, when you design a product to be used in real life, you also kind of care about how strong that product will be. If you're designing a chair, you need to make sure that the chair isn't going to break, even if someone sits on it, even if someone stands on it, even if someone knocks the chair over. You need to make sure that it's actually strong enough to withstand all of those loads. So another way that CAD is used is then to kind of take that model and perform some analysis on it, see what the maximum stress, see what the maximum loads are that you can apply to it. You can see how heat will transfer throughout the system. If it involves fluids, if you're designing like the idea is like you can basically kind of analyze it in usually another software package to determine how your part will respond to different environmental conditions. So these are just some words you'll hear thrown around, like computer engineering, finite elements, like computational fluid dynamics. These are things that you can try to look into, especially if you're on the older side, like in high school maybe. These are things that you might start hearing about or seeing and are definitely interesting to try to check out. So that's all I have to say about that. If you have any other questions about where you might use CAD, what you might do with it, let me know. And if there are no questions about that, I'll take questions about our project. So the homework from last week, I know some said that they didn't do it, but I'm sure these were pretty challenging parts. So I understand that you might have any questions there. But at this point, in an ideal world, you'll have made these components, which are all the components that you need to make the engine. But I know in real life, that's not always the case. So we have our
I
we have
only
our
did the
backups.
first 4. I forgot to do the upright and the flywheel.
Yeah, that's fine. And I think most people would have questions with these two parts. So I might not go through them all the way because that'll take a bit of time. I see in the chat, there's one question. I have troubles making the holes for the upright. Which holes in particular do you want to talk about?
The ones that have like threads.
Okay. So you're fine with like locating the holes, like with drawing your sketch points to tell Onshape where to put the holes. Just using the hole tool is the issue.
Yeah.
Okay. Was it these two?
It was those two and then the top left. Yeah.
Okay. Yeah, I'll just make a quick little block here. Let's see. It's 2x4. By 3/8.
Wait, how thick is it supposed to be again?
You can check the drawing. If you haven't done it, I'd say you can try to do it on your own time, looking at the drawing, because I think that's more helpful for you. Okay. All right, so we have our hole tool. And so let's see, let's look at this first hole. So the call out here is the symbol here, that like circle with the diagonal line through it. That's a symbol that means diameter. So what that's saying is diameter is 0.125. And then the word through means the hole goes all the way through. And then 1032 thread. It's like the diameter and pitch of the tapped part, and then 0.25 deep. That means the thread goes only a 1/4 inch deep, even though this first part, this 0.125, goes all the way through. So yeah, I guess that is pretty confusing, but in the side view here, you can kind of see what's going on. You have like that smaller diameter hole that's an 1/8 inch that goes all the way through, and then you have the wider part with the threads that goes in only 0.25 of the way. And if that's ambiguous, you might not know like what the diameter of a 10 is. One thing you can do, I use these all the time, is consult a, not metric, but a standard tap chart. And these will tell you that for a screw size 10-32, the threaded diameter corresponds to 0.159. So you can use a chart like this. I know that 0.159 is greater than 0.125. So it makes sense to me that the first part of the hole is going to be deeper than that part. So yeah, I can just do this in 2 features. So the first part is just going to be, let's see. Just make it a clearance. I guess the smallest size that they offer me is bigger than what I want, so I'll just make it a custom 0.125 that goes through. That's the first part of my hole.
Yeah, I'm not supposed to use ANSI for this, right? Or am I supposed to use custom for both?
Yeah, you can use custom for this one, just because I
Also,
didn't see.
Oh
anything.
yeah, that reminds me of something. I had like sort of a problem, but also not a problem on the crank wheel.
Sure.
So basically, in the recording, because I wasn't there, it said that I should use ANSI with thread and 32, but then that didn't work. And then I just tried I just clicked on hole and then pressed the check mark and it worked. I didn't change anything. All it said was a custom and like a number.
Sure. Well, we'll talk about that in a bit.
I don't know how it works.
So what you can do to make 2 holes in the same spot is, like I've mentioned before, when you have, whenever you create a feature from a sketch, Onshape likes to hide that sketch automatically. But the way you can unhide that is by hitting the eye icon that appears in the feature tree. So if the eye is crossed out, it means it's hidden. If the eye is open, it means you can see it. So that brings this point back, and I can just make another hole in the same place using the same point. But this time I'm going to do a 1032 tapped, number 10, 32 threads per inch, and to a depth of 0.25. Oops, what happened there? Let's take a look at that. For merge scope, you can just hit part 1. It's kind of asking you, where should I look to combine this feature with the rest of what's already been made. It's nothing special there, but yeah, you can do something like that, and you have 2 holes now And you can see like this is the top like threaded part. This is the bottom through hole. And I can just go back and hide that sketch again if I don't want to look at it. But there you go. Now, a lot of CAD programs, they have what's called cosmetic threads. So you can notice, even though this is like actually a tapped hole, that it looks smooth in my model, right? And that's because when you actually create a 3D model of those like screw threads, it just adds a lot of geometry that can slow down your computer if you have a lot of them. So by default, most CAD packages, and including Onshape, they just they don't show you the actual threads. They just show you either the major or the minor diameter with the threads. But some programs have the option to turn on what's called cosmetic threads, and then you can actually see the threaded geometry. And to finish answering your question, I guess there are these two holes. Do you think you're good with these? It's the same idea. It's just that.
Okay, I'll try it.
Yeah.
Wait, are those two holes the exact same, but they only numbered one of them?
All right, these two should be the exact same.
Oh,
Although what's
okay.
interesting here is that it's a 530. What is 532? Let's do some quick calculator. Yeah, 0.156. So as you recall from the tab chart, actually I don't recall from the tab chart. For 1032, right, the pre-drill for a 1032 is 0.159. So it's happening here. 532 is 0.156. So if you're making this in real life, what would happen is you drill in 0.5 deep using a 532. And like these tab charts, they're not like absolute, like they're like basically you should follow them, but there's so many different types of drills in real life that you can usually get away with using a drill that's like very close to the size you're using. So in this case, instead of using a 0.159, they're using a 530 seconds.
I have a question.
Let's see. Yeah, so instead of a 0.159, like they're just saying like use a 530 seconds, and that's your pre-drill. So your pre-drill goes in half an inch. This is a bit of a weird call out. Like I can understand why this would have caused some confusion. And even if you were machining this, I would be a bit confused by this call out. But you can ignore the 530 seconds part. That's just what you'd use as the pre-drill. And then you would actually go through again with that tap that I showed you to do that 1032 thread to a depth of 0.5. So I guess the reason they might have said it is they just really want to make sure you get the threads 0.5 inches deep, because you do need to drill a bit deeper than your tap in most cases. But yeah, don't worry about it is the conclusion.
Wait, both of them are tapped?
Yes.
And my second question, like, what are those small, like, construction line things at the bottom?
Right. So these lines, or wait, sorry, which construction lines?
Like the one you were just hovering over.
Here.
Yeah.
Yeah. So they're hidden lines,
Wait,
as we talked about.
do we have to use them?
Well, you'd only use hidden lines if you were making a drawing, which we have not covered in this class. But
Are they like useful in some way?
well, they're showing you that there is a hole there, right?
Wait, what?
Like without these lines, you're not. Oh,
Oh,
are you
yeah.
talking about the blue line?
What?
I'm not sure which line
No,
you're
no,
talking about.
wait, is it like how deep the circle's supposed to go?
Yeah, the depth of these holes is indicated twice. So you have this 0.5 here, and you have this 0.5 deep in the hole call out.
Oh, okay.
All right, is there any other question about any of the parts? If not, I guess we can start our assembly. So as before, it took a moment to upload.
Yeah, can you quickly show like the flywheel? Like because if I can't download it because mine's are in everything I'm doing is in centimeters, so and I can't change the download.
If you want, you can just download all of them and use those to practice the assembly while we're here together. And then on your own time, if you want, you can go back and try to model everything for yourself and then assemble your versions.
Can you just
Um,
quickly go over it or no?
it's pretty similar to that second demonstration I showed of the crank wheel where you draw like the profile. Like I drew like that L-shaped block and then I revolved it around the axis. In this case, you would draw like an I-shaped block, the one that's here. So I won't really do it, but to give you, since you might not have seen that part of that class.
You mean last class?
Yes, the one when we did the crank wheel.
Oh, I wasn't here last class.
All right, I think the recording is out there,
Yeah, I was.
but like it's the same idea. Instead of making an L, you make like an I shape. And then you revolve, like you make sure you dimension you dimension this whole eye using the dimensions here and using half of the diameter as the distance from your axis of revolution to that feature. And
Did you make that construction line?
Yeah.
Wait, we're supposed to make the construction line there?
You need a line, but I like to make it a construction line because it's not actually part of the part.
It doesn't matter how big it is, right?
It doesn't matter how big it is. You should follow the drawing so that it actually matches up with the rest of your parts, seeing as the drawing is intended for you to make the parts so that they end up fitting together. But this is the idea, right? If you make an eye shape and then you revolve it, you're going to get this kind of disc with two rims. And then you just these holes a lot of the time are simply not needed for us when we're making 3D models. When you're making it in real life, you want these to put in things like set screws.
Wait,
like this tiny hole here, right? Like that's for a set screw.
Wait, that was it for it?
Yeah, that's basically it. You make the eye, you dimension it with the proper dimensions. And if you want to like completely do it, you can add this set screw hole here. But otherwise, it's just a 2-feature part, basically, right?
What's the set screw? Is it like a circle and then you put it?
Yeah, a set screw is basically like just usually a pretty short screw.
Is it tapped?
Without a head. Yeah,
is it tapped?
Yeah, you can see the threads. You didn't say that it's tapped. A tap is a tool that you use to make female threads. So this is like a male thread, right? And so these would usually be made perhaps with a tool called a die. So it's like you can buy like die and tap sets at your hardware store. The tap is what you use to make the female threads. So if you have a hole, you tap the hole to cut the threads along the hole. And then if you have a rod, you use a die to like cut the threads out from the rod. So in this picture, like the person is starting out with a rod and then they twist it into the die, and the die, it's basically the same thing as a tap, just the complement. You can see it has these cutting edges inside. So as you twist it, it kind of cuts these threads into your rod. So I don't know if that's how they make screws in real life. I imagine it's something like that. But the idea with a set screw is you have like this tiny hole that goes through. You probably have a shaft that goes through this flywheel, and then you screw the set screw perpendicular direction into the shaft. It doesn't actually go through the shaft. It just like pushes really hard against the shaft. So then you can't pull the shaft back out because there's this set screw that's reacting against it with friction. So it's a lot of pressure.
Which surface do you click on to revolve it?
The sketch profile is the eye that you drew. the axis of revolution is that line.
No, I'm saying when you revolve, which face do you click on of the flywheel?
You're clicking on that I shape. Like the letter I, not the human eye, right? Mine didn't really click an
okay.
eye, but yeah.
Okay.
Anyway. Yeah, so go to Google Classroom if you're missing any parts, and very high chance that you are if you just did one of the upright or the flywheel, which is why I'm providing them. So at minimum, you're probably downloading either the flywheel or the upright, and at maximum, maybe just download all of them so that you can start a new assembly. And I'll take a second to do that myself. Sorry about that. Actually, what am I doing? I uploaded these files myself. All right, so yeah, let me know when you're good, but you should have 6 parts. The flywheel and the download has a bit of a cosmetic pocket there. That's just so you can see it spin better. When it's a solid flywheel, it's a bit hard to see it that it's spinning. But total is 6. They are the base, the crank wheel, cylinder, flywheel, piston,
Oh wait, just a quick
and the upright.
question. On
Yes,
the upright, aren't the 2 circles on the top the same? Like the one above? Yeah, aren't those 2 the same?
these 2.
Yeah. Because they're basically even though one uses the hole and the other doesn't, it still uses the same concept.
They're both 1/8-inch holes. It's just that the one on the left has threads up to a 1/4 inch depth. So this one is going to be taking a screw on one
So there's
side.
a thread up to a 1/4 inch, up to a
Yeah.
1/4 inch.
For our model, it's not really necessary, but in real life, you'll see that it is necessary because what you're going to end up doing is, I believe that's where like a fitting goes for a tube for the
Wait,
air to go to.
wait, is it?
So you don't really need it. Yeah, it's tapped. This is the first demonstration I did in this part of the class. You can just add another hole in the same location, but for the model, it's not really necessary, and I didn't do it in the
Wait,
ones you
what's
can
the
download.
tap clearance? Is it just 3?
Tap and clearance means there are no threads.
Oh,
Clearance means it's big enough for the screw to just slide in and out of. Tapped means it has threads, so you twist the screw into it. All right, so if you have all the parts, we'll start working on the assembly. So it's kind of I think the PDF that I put up has a diagram of what it's supposed to look like. Yeah. Right, so this is what it's supposed to look like. Kind of have a visual reference. So if you're an adventurous type of spirit, you can try to assemble this thing on your own, come back, see how you did. Once you understand the concept of how this engine works, it'll probably be pretty straightforward, but I'll just do a little demonstration and try to explain what's going on as I do it. So the first thing you do, you open up your assembly. You can create one if it's not there. By default, you should have assembly one, as we usually do. And I'll just click and add one copy, just one of every part, making a total of 6 components, and hitting the check mark, which tells Onshape, yep, this is what I want. And as I've hopefully emphasized a few times by now, the first thing I usually want you to do when you create an assembly is to fix a component. You can use the fasten mate, but you want to make sure that some logical part of your assembly is located in a logical way with respect to this point, the origin of your assembly. So what I'll do, start off, is use my old fasten mate, and I'll just make it so the bottom center of the plate lines up with the origin. So that's my first assembly mate. You can see now I can't move around this base plate even if I drag it around, unlike these guys, which are all free to move. I'll just hide my origin there, just because I don't want to look at it.
Wait, there are threads in that one? In
Yeah.
the upright?
Yeah, these have threads, and this one has threads.
Wait, I don't see any threads though.
Right, like I was saying, in CAD, usually the threads aren't modeled just because it's almost never useful.
So can I just, so for
Yeah,
the
for the
whole,
assembly, you don't have to do them. Like for the 3D model, you don't really have to do them.
can I just like, when the whole, I just put it as it is, because if I put it as it is, it just does it for me and I don't have to do anything.
I'm not sure I completely understood the situation, but if it works, go ahead.
But I
Our
don't think
main
there's any
goal
threads.
here is to
though.
do the assembly.
I don't
So
think
I'm
there's
going
any
to
threads. Does it matter if there's
move on
threads?
with that. No, like I said.
Okay.
So first things first, let's see. Actually, we have a handy reference image. But this, you can see why it's called an upright, because it's standing upright against your plate. So what I'm going to do is I'm going to fasten, whoops, that is not the connector I wanted. I'll just fasten the bottom of this hole to the top of one of these holes. Now, very interestingly, you can see that this version of the plate that you download, it has the counter bore. So let me do this properly. The bottom of the plate is actually the side that has the counter bores. So my bad there. And the reason for that, you can imagine, like I said, the counter bore is there, so the head of the bolt can sit on the part and be flush with the bottom surface. So the bolt's going in this way through the bottom where the counter bore is. And then it's threading into here. So the reason this hole is threaded is so that the screw can come in through here, and then the part that sticks out is threaded, and it would thread into the upright. Now, whenever you assemble things, when your mate connectors aren't oriented properly, you'll get things like this where nothing is right, but you can readjust your mate connector, effectively the orientation, just by hitting these 2 arrows in combination. And when it looks like the way you want it to, You can hit the check mark, and this is what it should look like, right? You have the upright, and it's standing upright on your base. So now these two holes have been used. There would be a screw here, but you can kind of see how it works. The head of the screw kind of sits inside of this counter bore, and then the threads go in and like they engage with the threaded part of the upright here. So if you didn't model the threads in the upright, which you may or may not have, you'll have to take that into account. But if you didn't model them, like I have not here, then it's symmetric now. So you don't have to worry about which side is which. But if you did do the threads, the purpose for the thread is for this little fitting here. So it should go on the outside. So the side with the flywheel should be the same side with that thread. But again, like if you don't want to think about it, don't worry about it. So the next thing we'll mount, let's see. Let's mount the cylinder. So this thing here. So what the cylinder does is it's held up by the upright and it's free to rock back and forth. The motion of the engine is like a rocking motion. So the cylinder is going to be pinned to the upright at one point, and it needs to be able to spin back and forth. So we need a mate that allows that to happen. It allows it to spin, but not to move around in space. So to me, that sounds like the job for the Revolute mate. And I'll just simply click on that hole and this hole, the one in the middle here. Then I'll use these arrows to adjust. But now there's my cylinder. I want the bore of the cylinder to be in the bottom. I want the bore to be at the bottom. And to verify you did it correctly, the base and the upright, you shouldn't be able to move at all, but the cylinder, it should be able to rock. All right, next is the piston. And so like when I was demonstrating the slider, I was saying like the classic example of this is a piston and cylinder. And here you go, we're making one, a piston and a cylinder. So this is the slider mate, and the way this works, if my memory serves me correctly, you're gonna wanna click on the normal face to the axis of motion. So the piston is going to be moving along its cylindrical axis. So I'm going to click on the circular face because that's perpendicular to the cylindrical axis. And for the other mate connector, I'll just, I think I can just click on this circle and at the bottom of that bore. I can also click on this circle at the opening. Shouldn't matter either way. And I want the head of the piston, I want the thick part to be going in. So not the other way with the thin part, but the thin rod should be coming out of the cylinder. So I'll hit the check mark on that. Now to verify that it's working, this is the action you should have. When you try to drag it, it can only move in and out. And like it can go through, but that's not going to happen when we're done. At the same time, the cylinder can rock and the slider goes in and out. All right. So once you have that, the next part we're going to put in is the crank wheel. So that's this guy. And the crank wheel goes in through this hole. Now in real life, you'd have some kind of shaft that connects, like that supports the crank wheel to this axis. So you can see in real life, they just use the bolt as the shaft. The head of the bolts is here on the other side of the flywheel. You can see it kind of go through the crank wheel. But yeah, for anything bigger, you'd probably just make a proper shaft for it. But again, it's the same situation. We want a revolute mate because it can spin freely, but not move. I'm gonna connect the top of the thin part, like the top of the hat, the top of the cake, and mate that to the surface of the upright. And if you have it going the wrong way, they're going through each other, you just hit the big arrow, that flips it around. I'll hit my check mark there. So now you can see crank wheel, it's like offset from the upright by that little boss there. And I'm able to spin it. And now to finish off this part of the assembly, what I want to do is make these two holes coaxial. But they also are able to rotate against each other. So I'll use a revolute mate. Now let me see. I believe these are designed so that these two parts touch exactly. There actually is a small gap, so. What you can do, as we did for the U-joints, is use a cylindrical mate. So that gives you the freedom to have them offset at an unknown distance from each other axially, but still have that feature of the revolute, which is to spin freely. And cylindrical, again, you just need two cylindrical parts. And then you can see they kind of jump out in a way that I don't expect it to. So to see how it actually look in the preview, I can tell Onshape to solve it. And this is the solved state. This looks like what I want. So I'll hit the check mark. And hopefully now, when you spin the crank wheel, what will happen is you get this reciprocating action where the piston is being drawn in and out of the cylinder as such as you spin the crank wheel.
Wait, when you spin the crank wheel, why is it not like attached? It's just like, oh no, wait, never mind, I see it.
Yeah, it's hard to see. It would be a lot more clear if we had the hardware modeled, but you know, be a lot more work too. And we're almost there. I'm gonna speed through this because I just realized how we're doing on time. But at this point, it should be pretty clear. You make the flywheel revolute with respect to the upright. And here's one kind of new thing that we're going to do, which is lock the flywheel to the crank wheel. The reason you need to do this is because otherwise the flywheel just spins on its own, which is not the intended behavior. Let's see if I remember how to do this. I believe actually you can just create a group. Yeah, so let me show that one more time. You can use this tool here kind of in the middle. It's called a group. And if you group multiple parts together, it's the flywheel and the crank wheel, for example, then they'll kind of move together. You can see now when I spin the flywheel, the crank wheel is also spinning because they're kind of grouped together. And so that's the entire motion of the engine. The way this would really work is the air would be driving the piston back and forth, and the linear motion of the piston within the rocking cylinder is what creates the rotation of this crank wheel. And then the crank wheel drives the flywheel. So what's really happening here is you're putting in air to create this kind of rotation of the flywheel. And the way that works, you can see in the image, through one of the sides, that's your inlet for the air. So let's say it's this side. So when these two holes line up, the air is going into the cylinder. And as that happens, the pressure of the air is going to push this cylinder out further. And as that happens, it rotates, gets into this configuration, and then these two holes line up. The air that's in the cylinder is going to be let out of this hole. And so as that happens, the piston kind of is able to get drawn back in a bit. And so it just goes back and forth between those two states. It's either getting air from this hole or letting air out of this hole. And as it continues to do that, it just spins this, and the result is the spinning flywheel. So that was our assembly.
Can you show me the flywheel? I want to try it myself. Like, I'm just gonna
Yeah, the drawings are all in Classroom, so you can go and look at those. Since we
Well,
are
can
approaching
you,
the
like,
end of our,
quickly show me like the sketches so I can like take screenshots.
like the sketches will basically be what you have in the drawing.
Because like I don't really know how to like make it.
I'd say it's very similar to the crank wheel demo from last class. If you go watch that one, you can see like how I do all the dimensions for the diameters just by going from the construction line to the edge of the feature.
How do you make the like the 3 circles inside of it? Like the 3 like sort of triangular circles inside of it?
Which I'm not sure which feature you mean.
Like when you were
Here,
doing
we can talk about this in a few minutes. For the rest of you, next week we're going to be, like I said, talking about it's just some topics in 3D printing. I'm by no means an expert, but hopefully I know a little bit that I can teach you. And we're going to move on to our last project, which is going to be designing a little trinket, a keychain of some kind. So come back next week with some ideas, like the rough size of it. If you do print it, perhaps try to keep it within like 2 cubic inches. So that's that. As always, thanks for coming, and I'll see you again next week at the same, hopefully same time. So if you have any last questions, I'll stick around if you're going to ask one.
Thanks. Bye.
Yeah. So